Here we go. We're live again. So I've got a question for all of you. Give me some of the top YouTube influencers out there. Give me a couple. That's not fair. That one doesn't count yet. Come on, give me a couple of YouTube influencers. You're telling me you never watch YouTube? Yeah. Jordan Peterson. Okay. Some other ones? PewDiePie. Okay. So what I really want to know is I want to know who are the top 10 YouTube influencers by their view count. And so Riley actually got the right answer. There's number 1 over there. But other than that, that's going to be our topic for today, is we're going to have a list of view counts, and we're going to want to put those view counts in order so that we can finally decide once and for all who is the number 1 YouTube star. And to do this, we're going to build on our tools from yesterday. We're going to use pointers. And yes, we are going to use arrays. This is very exciting because all of you have been asking me, when can we use arrays? When can we use arrays? Today is the day. So to start off, we're going to go back to our pointers and build up our technical skills a little bit so that we can actually use them to perform some of the tasks that we'll need to solve our number 1 influencer problem. So with that, let's kick over to a code demo. So this is just some basic pointer syntax for us to go over. I'm going to have a static integer w. That's just a normal integer. We've seen this plenty of times before. I'll have 3 other integers, x, y, and z. And what I'm going to do is I'm going to convert them into pointers. Now, when I say convert them, I don't actually mean that the type of the variable will change. Those variables are going to be the same no matter what you do to them because C is statically typed. But what I am going to do is get their addresses. And those addresses can then be stored inside a pointer in our next example. So let's give this a run. Clang pointer1.c. And there I have my 4 different addresses of the variables printed. Why did I get the addresses and not their contents? It's because I used the ampersand symbol, which we talked about yesterday. The and sign gets you the address, where a variable is located inside the computer's memory. And just like in our layout demos, the static integer is located in a different place to the other integers that are located on the stack. When we want to print a pointer, the other thing you'll also notice in this demo is we are using the percentage sign p flag to indicate that it's a pointer type that we're printing out, and 16 because that is the width of an integer on this system. Okay, pointer1 demo, simple enough. We've taken a bunch of variables, we've looked at their addresses, and we see they are organized the way we would expect. Pointer demo 2. Okay, we're upping the level of difficulty a little bit here. I now have a number, an integer n that I'm declaring, and I'm also using this weird declaration syntax followed by a comma, which means declare something of the same type, and this time because we're using the star in our declaration, we're going to make this a pointer. What kind of a pointer is it? It's an integer pointer because at the very start of the line is int. Okay, then we're going to declare a double x, and we have another pointer, pd. It's a double pointer. Okay, we're going to print f, just print out our variables. Then we're going to, what are we going to do here? We are going to take our 2 pointers, and we're going to fill the pointers with the address of our variables, n and x. So remember in our past example, if we use the ampersand, that gives you the address of something. And once we get the address of n, we're going to want to store it inside a variable. What kind of variable stores an address? A pointer, yeah. So we are storing the address of n in pi and the address of x in pd. Then we are going to print star pi and star pd. Now when I do the star, what does that mean? When I use the magic star of dereferencing, dereference. So this is going to allow us to follow the pointer to the location to which they point. So let's see, who haven't I spoken to? Daksh. When I dereference pi, what is the computer going to print out for us?
The value of n?
Yep, the value of n. And what's the value of n?
1, 2, 3.
1, 2, 3. Sorry, I couldn't see where you were for a second. Okay, and for pd, what are we going to print out?
The value of x, that is 465.789.
456,789. Almost. Okay. Then our next step is to take pi and calculate pi plus 1. Now, one of the interesting questions here is only pi going to be changed, or is n going to be changed? What do you think in this instance?
N is going to change. I think n is going to change.
Think n is going to change. Okay. Why is n going to change in this instance? Dash
Also
still.
because we change the value at the pointer location.
Yeah, so Daksh is right. What we're doing here, our syntax is interesting. What we're doing is we're not modifying pi itself. What we're doing is we are dereferencing pi, and at the dereferenced location, we are going to store what was previously at the dereferenced location plus 1. Same kind of thing is happening in this next line. We're going to figure out what PD is pointing to and get that value. We're going to get the value of pi, and we are going to store that at the location pointed to by PD. So remember, whenever we have the star, that means follow the pointer to the location. And so if we're storing something, we're storing it at the location that we've followed to. We print them out, and then we return 0. Let's give this a run. So as Daksh said, first we just print the two variables. Then we dereference them and print their values. Now what we've done is we've added 1 to star pi in this line over here. First we dereference it, we add 1, and where do we store it? We store it at the dereferenced location. So star pi is 124, but also n is 124. We've actually gone to that location and changed what is at that location. And we've also done the same to our double. Okay, great. So this shows us how to use pointers, but we still haven't done anything interesting with them. We're no closer to solving our #1 influencer problem. So let's move to something different. In order to build up our sorted list of people who have the most YouTube views, we have a list of the views that everyone's seen, and I want the list from biggest to smallest, right? But they're right now all out of order. So what do I have to do to get them into order? Not Oscar, sorry. In the Tommy Hilfiger, what was your name again? Melissa. So they're out of order. If you want to figure out what they'd be like in order, what do you have to do to them? Sort them. And how do you sort things that are out of order? And then what do you do if they're out of order? You swap them. Okay, so we need some way to swap things. Let's see what our swapping code looks like. So here's one version of the swap code. I have two values, x and y. I'm going to just read them in from the user. I'm going to run the swapping function, and then we'll see what the values are. Now this is what my swap function looks like. My swap function takes in two values, x and y. It makes a temporary copy of x. So let's say that x is 3 and y is 5. We're now going to make a temporary copy of x. So x was 3. So temp is now 3. X is now 5. And then y equals temp, so y is now 3. And we're done, right? So my print statement here should now be x is 5 and y is 3, right? Yeah? Okay, let's give it a run and see what happens. Enter value of x, let's do 3. Enter value of y is 5. Oh, this is a bit funny. When I swap them, I have a print statement here that says after swapping them inside swap 1, I have 5 and then 3. But when I went back to the main function, it's 3 and then 5. That doesn't seem to work right. Ashwin, what's going on here?
The scope, so the function, it's its own separate thing. It's not actually changing the value.
You say that again a bit louder?
It's the function, it's its own separate thing. It's about scope. So everything done in the function doesn't actually affect the main.
So who's next to you? What's your name? Du? Okay, so Do, remember I said something when we were learning about scope. What happens when we give an argument to a function? What happens before the function starts to run? So remember I did the demo with the 2 sheets of paper where I had my main function and my new function? It makes a copy. So all we've done is we've made a copy of x and y, and we've swapped what's in the copies, and then when we go back to main, what's wrong? If we've swapped the copies, what's happened in our main function? Nothing. Nothing's happened at all. Our copies have been swapped, but they've just been destroyed because that function is finished. We get rid of those variables, and we're back in our main function, and nothing's changed. But we're smart FOA students now. We've got new tools. So let's look at swap2 and see how we can fix this problem. A new swap function. Now we have 2 pointers that are going to be the arguments. So if I give a pointer to a function and do, okay, so we're in the same situation as before. I'm calling my function, only now instead of x and y, I have a pointer to x and a pointer to y. So what happens when the function starts? It copies, yeah. And so what is it copying? It's copying the pointers, which means it's copying the addresses. So now inside of the swap function, we don't have 3 and 5. What we have are pointers to where 3 and 5 are stored, which means that if I change the value pointed to there, will I see it reflected in the main? Yeah, because I'm pointing to something elsewhere. And so when my function is destroyed, when it's popped off the stack, what I've changed over there is still there. And it's still the same thing as it was in the main function. So let's look at our overall code again. It's the same here. I've entered 2 values, and now I've called swap, and now I've done something different here. In order to create pointers out of the variables, in order to get their addresses so that I can give the addresses to the swap function so that the swap function can copy them, I've now used the ampersand, because what I want to give swap, I don't want to give swap 3 and 5, because then it'll just copy 3 and 5, and then it'll swap them, and then nothing will have changed. What I want to give swap is the location of where x and y are, so that when it swaps what's at those locations, it's the original places that have changed. So to do that, I've used the ampersand symbol again, and now I have given swap the location of x and y. It copies the location into the swap function, and then we can use it as we please. So we've copied the location of x and y into our swap function, and now let's write it out on the terminal here so that I don't have to mess with the iPad. So let's say we have address xp is 50, and let's make yp is 60. It's just demo values. I know they're not the real ones. Okay, what does my first line do? I need someone new who I haven't. Emmeline, you haven't answered in a while. Okay, and let's give you a microphone because you're pretty far back. Okay, Emmeline, what does this first line do?
In the swap function,
Yeah, in the swap function, this highlighted thing on line 8.
it takes the value pointed to by xp and assigns it to 10.
Yeah, so let's say we're using the same numbers as before, where x was 3 and y was 5.
Yeah.
So what happens?
Assign 3 to 10.
3 to temp. Okay, so we have temp is now 3 because star xp is 3, right? Okay, next line.
It would assign 5 to the location pointed to by xp.
Now set star xp to 5. So that means that the original thing, whatever xp was, and let's see what xp was. xp was the location of x, so the original x in this main function now has its value set to 5. Next line.
It assigns 10, which was the original value of xp to y. Well, star yp.
2, 3, right? What it was before, and then we just print them inside, and we throw out the copies, and we go back, and then we print them again. Okay, thank you very much, Emmeline. Let's give a run of this one. Call that swap2, enter value of x, 3, 5, and now you can see that our swap function has actually worked. Very round of applause for Emmeline, please. Thank you very much. You can pass the microphone back. What are the values of the following variables if this is all the code? Okay, what are the values of the following variables? Okay, so int a, what is the value at a? Do you have a guess? Why would it be 1? You can answer. Guess, it's fine. So I haven't added anything to it yet. All I've done is a declaration. So what was your name? Jared says, maybe it's 1. Actually, Jared could totally be right. We actually haven't put anything in that location, but it's still somewhere physical in the computer's memory. So whatever was in the computer's memory there before is still there. So if you have not assigned something to a variable, it's not necessarily 0. It might be 0. It might be 25. It might be 56. It might be 1. So Jared was actually, your guess was totally fine. It could be 1. What about the next one? Int star b equals address of a. Holding your phone up, what's your name? Oh, I guess multiple people are holding their phone. Nelson, we'll go with you.
Will save the pointer address.
It'll save the address of A. And this works even though we haven't actually put anything inside A, because A is just a location in memory. It could be filled with whatever the computer left there before. But its address is still a well-defined thing, because we've set up a location, and now we've just gotten the address of that location. So that's something to keep in mind. And now that we have all our tools together, we finally get there. We have our array, and this is going to start making life more interesting because it's going to allow us to play with data in all different ways throughout our course and to build up our list of all the Instagram views and then finally get me to reign supreme as the #1 influencer. Okay, so an array is just a collection of objects, and in C, all these objects have to be the same. Why might they have to be the same? Yeah, well, I've forgotten your name. Haruki, yeah.
Because different data types can have different byte width.
Yeah, so Haruki says different data types take up different amounts of room in memory. Remember that a byte just takes up a character takes up 1 byte, but an integer takes up more than 1 byte, which means that if we're mixing them, then we're not going to have this beautiful, easy, cleanly spaced group of elements. So C, instead of hiding the complexity from us, makes sure that we can only do the right thing in this instance by grouping objects of like types together, segmenting memory in clean and even divisions. Other languages might allow you to mix things, but really behind the scenes they're going to have chunks where like a chunk of 1 byte, a chunk of 4 bytes, a chunk of 8 bytes, and that can be very inefficient. So C restricts us to this kind of like type of objects. So it's a linear collection of like objects, so they go in a straight line through computer's memory. So if they're 1 byte objects, you might have something at address 1, address 2, address 3, address 4. If they're 4 byte objects, you might have something at address 1, address 5, address 9, etc., etc. And here's just a nice example of an int array. And we'll see one of these live before your eyes in just a few minutes. Most of the data we want to analyze comes in more than 1s and 2s, so it's going to make a lot of sense for us to use these. A lot of you have already been chomping at the bit because you're struggling to get things done. What if I want more than like X, Y, and Z? What if the user enters 5 variables? How am I going to store all 5 things? The array is the answer to that. An array is a data type in C, so it's a type just like char, int, etc., and it's going to have corresponding declarations that you can use to actually create one. But it's also a data structure. And what I mean by this is it's an abstract object that we can think about in a more complicated way than just an int. So an int is an int. You can read it, or you can change it, or you can mix them together. As a data structure, we can now think about more complicated things that we can do with arrays. So we can set certain rules about how we use them. We can process data in sophisticated manners. And that's what we're going to see today through our introduction to shorting. So you might think that arrays are boring, there's not much to it. But they're actually really, really useful and underlie a whole bunch of the more sophisticated data types and a whole lot of the more sophisticated abstract data types and data structures that we're going to see in this course. But one interesting thing in C, arrays are just pointers. They're just pointers. It's with a different syntax. Why might it be easy to interchange them? Victor.
Because like in each index will have its own memory location, and so it's when you have an element in your index, it's basically storing that element in a particular memory location.
Yeah, so Victor says, what pointers do is they allow you to access memory, and if you add 1 to the pointer, it's going to take you to the next spot, and if you add 2 to the pointer, it'll take you to the spot after that. And that's really all that's happening with arrays is we're going from one spot to the next spot to the next spot to the next spot to the next spot. And so what C has actually done is they've tidied up the array syntax because it'd be a bit confusing, and it's even for me, I can have difficulty with the magic star of dereferencing. So instead we add what's called syntactic sugar. We use our idea that we had before and we dress it up with some new syntax. So this is the array syntax that we are going to start to use. To declare an array, you have the type, then the name of the variable, then open square brackets, the size of the array, and then close square brackets. You can also allocate it and initialize it at the same time using this curly bracket syntax. But don't try to use the curly bracket syntax to assign elements to the array after the array's already been created. It won't work. So you couldn't do line 1 and then line 2, even if you take the word char off line 2. It's just not going to work, not allowed in C. We also have the ability to create a pointer to the start of the array, which is really just saying, okay, where is the first place in memory at which these elements are located? And then what you could do is you could go to the next element, and the next element, and the next element using the pointer, or using the array syntax. And notice that in this case, I didn't have to use the ampersand operator, as I say up there. This might be a bit weird. Why is it not weird? They're both addresses, right? They both tell us about a particular location in physical memory. And so it makes sense that if I create a pointer, that I can just assign the array to the pointer, because what the array really is it's just that location in memory, and it's just some syntactic sugar covering it up. Here's a diagrammatic version of it. You can see if we have our variable a, it just points to some location in memory. That's the start of the array. And if I ask for array element 3, we would go 0, 1, 2, 3, and I would get this element here. So notice I nearly stuffed up there. Arrays in C are 0 indexed. So the first element over there is element 0, that's element 1, that's element 2, and so on and so forth. Part of the reason we do 0 index them is so that it makes sense with the pointer. So array element 0 is really just star of a plus 0. Array element 1 is star a plus 1 in parentheses to make sure that you're dereferencing the pointer plus moving on to the next address. So we've already talked a little bit about this. What happens if you pass an array to a function? So this is just like our example before, where if you pass a pointer as an argument to a function, I need someone new who I haven't spoken to before. Okay. Aquaish t-shirt in front of Emmeline. Yeah. What was your name?
Dat. D-A-T.
Dat.
Yep.
Okay, so if I pass an array to a function as a variable, what is going to happen when I start the function?
So it's going to copy the address of the array.
Yeah, that's a really good answer, actually. So you might have thought that if you pass an array as an argument to a function, it copies all the data. But this is actually one of the subtleties. Because what arrays are just actually pointers pointing to somewhere else in memory, the array itself doesn't get copied. What gets copied is the address of the start of the array, which means then you need to be careful about doing operations once you're actually inside your function, because if you use array syntax, you'll still be accessing the memory of, will you be accessing a copied version, or will you be accessing the original version? Yeah, you'll be accessing the original version because you've copied the address in. But this is going to be useful for us. However, sadly, functions cannot return whole arrays. So if you create an array inside a function, you're only going to be able to pass a pointer to that array that you created. Now, why might this be a really bad idea? University of Melbourne hat. Yeah, name? One? Quan. Why might it be a bad idea to pass a pointer to an array that you've created inside the function in which you created it? So what happens when a function ends? What happens to the variables you created? So do you remember our example with the stack? What happens when a function ends? So we remove the top of the stack, right? We remove that part of the function. And in that stack, what's inside that? When, let's say I declare 3 variables x, y, and z inside a function f, what happens when I remove those from the stack? The variables are gone, right? So I no longer have access to them. So if I've created an array inside a function, and then I've passed a pointer to that array, well, all well and good that I passed a pointer, but that memory doesn't belong to us anymore. That memory now belongs back to the operating system, because the operating system has destroyed the place where it used to be. And by destroyed, I don't mean actually destroyed. It's just forgotten about. It's been reclaimed for use by other things. So what you can do is in the main function, for example, you could create the array, you pass the pointer into a function, then you change the array, and then you can pass the pointer back to someone else, and because the main function is still running, that array hasn't been destroyed. We'll also see some more sophisticated ways to manage memory as the class goes on, but for now this is one of the big traps to watch out for. So let's look at our array syntax. This is our warm-up exercise before we finally get to sorting. So this is just a very gentle introduction to arrays. I'm going to declare an array of length n here. And what is n? I've hash defined n to be 5 up there. Now, one thing you might ask is, how do I know ahead of time what size my array should be? One thing that's challenging about C is that in its normal usage, C requires you to know ahead of time how many objects are going to be in the array. So we have created our array of length n, which is just 5. We're going to do a for loop, and we're going to fill up the elements of the array using I as the index. Now, this is another key sticking point. The array index I here that's in the loop that's going from 0 to n is not the same as n itself. I see this mistake over and over and over. N is the size of the array, not the element that you're trying to access at the current time. So if n is 5, as we have at the top, and I'm accessing the 5th element of the array when I type in 5, is that correct? No. What was your name? It wasn't. Yeah. What was your name again? Yeah, I'm looking at you. Yeah. Crystal. So Crystal, if I access the nth element, and n is 5, sorry, if I do a of 5, and what number element in the array am I accessing? So what's the first element of the array? Is the first element of the array A1? Or is it A0 is the first element of the array. So if n is 5, so this is the first element is index 0, the second element is element 1, the third element is element 2, the third element is element 3, the fourth element is element 3, the element 4 is the 5th, which means if I do a of 5, that's actually the 6th element. And how large did I make my array? 5. So I'm now accessing an element that there actually isn't in there. So not only will this not loop from the first element to the element at the end, it's actually going to give you an error because you're accessing memory that doesn't belong to you. It's past the end of the array. So keep an eye out for that one. Okay. And then what are we going to do with this? I'm just going to use this to calculate a simple arithmetic sequence. There's nothing particularly interesting about the mathematics that I'm doing here. And now what I do here is I'm just going to loop over from 0 to n again. And notice here I'm doing n minus 1. Liam is giving me hints about interesting things to say at the back in very large on his laptop. I didn't see that hint. OK, we'll get to that after. When I do I is less than n, this means that I will actually never take on the value of 5 inside the loop. I will go 0, 1, 2, 3, 4. At the end of the loop, I will be incremented to 5. Now 5 is not less than 5, and so you'll never run this line with I equal to 5, which means we will print out index 0, 1, 2, 3, 4, and then we'll be out of the loop. So let's give this a run. Array 1. There we go. We've computed our arithmetic sequence. Now, one question is that you might have done this in Python. What happens if I ask for this? That should work, right? It's just memory. We could go backwards in memory. Unfortunately, that's not valid C syntax. you can only access from the start of the array because that is the memory that has been given to you. This is not like in Python where you could access like from the other end of it. C doesn't actually keep track for you how many elements there are in the array. It'll tell the operating system to give you the chunk of memory, but it's up to you to manage the indices. There's no fancy way to reverse them. You have to actually go from the back yourself and keep track of how many elements there are. So with that, we are ready to sort. And for this is going to be, I think, a highlight for me and hopefully for many of you. I need a whole bunch of volunteers. So hopefully people that I haven't spoken to yet today, Charlene, you're up for this for sure. Come down to the front, and I need a whole bunch more volunteers. Okay, Oscar, you can be up on this one as well. You two, just come down the front. Yep, what was your name again? Kit. Okay, come on. 1, 2, 3, 4, 5. And I need 2 more. Yeah, what was your name again? Perrin, that's right. We spoke. And your name was? Maria. Okay, I think we've got enough for everyone. Now, unfortunately, Charlene, you were unlucky in that I caught your name at the wrong time during class. So you're not getting one of these. You're getting something different. Okay, take a number. And take the pile.
Take the pile? Okay.
Yeah, take the pile and pass a number to everyone except Charlene. Nah. Okay, there should be enough numbers there for everyone except Charlene. Okay, well, everyone got a number, none left over? Are you in sorted order? Okay, don't put yourselves in sorted order. And Charlene, this is a big brain moment for you. You can hold it over your head.
Is it heavy?
No, it's not that heavy. But there is a helmet thing in there. Yeah, you put it on. It is a bit heavy. It's good enough. Okay, so Charlene is going to be our computer. And remember, we were discussing before, the way to get things into sorted order is to swap things one at a time. You can't just tell the computer, okay, magically, I want my influences to be in order of Maria's most popular. Oh, this isn't sorted order. Mix yourselves up. This is all wrong. Mix yourselves up. Okay. Phew. And Charlene, maybe put yourself Maria, sorry, put yourself somewhere in there. There we go. That's looking good. Hang there for a minute. So I can, as a human, I can see all of these at once. But our computer isn't able to see all of these at once and just like magic them into sorted. Our computer is going to have to use swapping. So our computer over here is going to, one at a time, and I'll move over the other side to give you a bit more space. You're going to give orders to all of our classmates and tell them how to swap. And the trick here, you should have a strategy for figuring out how to swap. I want the biggest influencer on this side and the smallest influencer on that side by their view count. And these are their view counts. So give me a second, actually. Where did the microphone go? Ahmed, I don't have that microphone. And Charlene, you're going to have the microphone so that you can let everyone know what we're going to be doing.
I cannot.
You can't do it? Okay, keep the brain, keep the brain. Put the brain on and I'll hold the microphone for you. It's a necessity. Okay.
And then?
Okay, now you give orders to who needs to swap with each other.
Okay, so the largest one, well, so number 9 swap with number 2. That is 9.
Yep, number 9 and number 2 swap.
7 and 1 as well. And then number 1 and number 4. And then number 3, number 2.
And we're done, right? Yeah. Okay, so, oh yeah, round of applause. So am I. So let's go into the order you were before. Remember how you started off. Go back in that scrambled order. Okay, now, in your big brain wisdom, explain to all of us here. It's very lovely to meet you. I'm impressed with your intelligence. Can you explain to our audience here how you managed to do that? What was your thought process? Tell us.
Well, it's just starting out with the biggest number and then finding out the second biggest number and putting them in the correct place.
So over and over and over, you were looking for,
The next biggest number.
yeah, the biggest number. So the biggest number that you hadn't seen so far.
Yeah.
Oh, that's very intelligent. So how many times do we have to repeat this process?
It just depends like where they started.
Yeah, but in the worst case, what if they were totally scrambled and in the wrong order?
Many times.
So would we have to do it 50 times?
No.
How many times can we look for the biggest thing?
6 times.
Yeah, so it seems to be that each time we look for the biggest thing out of all of them, and then we can do this a maximum of as many times as there are things to look at. Okay, now imagine that I've given you some blinkers, right? And now you're only allowed to look at one thing at a time, right? So let's go on and do this. Okay, show me how you'd look for the biggest number. You can only look at one of them at a time.
Oh, you can't like compare them.
You can look at one and the one next to it. We'll make that the rule. Oh yeah, flip your cards backwards. Charlene, so show me how we do this. You can go up to a person and get them to turn over their number.
Okay, so like,
So let's do it.
yes. Oh god.
So what are we doing?
So starting from like the leftmost. So like
The leftmost over there?
Yeah.
Okay, so
So
let's go over there. Let's start.
so like just show the
Yeah,
number.
come close, turn around a little so our audience can see you.
yes.
And
Okay.
So open number and then second.
yep, and you can look at the next
Yep.
one as well.
And then
And you can have them both flipped at once.
Yeah. So sort like whoever's the biggest one will stay to the left.
Okay, so we're going to leave. Do we swap or do we not swap?
We do not stop.
Do not swap. Okay.
Okay.
Now what do we do?
We
Okay, turn them over. We're done looking at you.
do I remember?
No.
Okay. So I open this one. Okay, and then open the next one. And then like whoever's the bigger one goes to the left.
So we do a swap
Yeah.
or not swap?
Swap.
Swap. Okay.
Okay.
Okay. Thank you. Turn them back over.
And then so you keep it open, and then open this one, and then whoever's the biggest one will go to the left.
And we're done. We're done. Okay.
These two will open. Yeah. And then whoever's bigger, swap please.
So you have to say swap or not swap
Yeah, swap.
because they're not intelligent. You're the intelligent one here. Yeah, swap please. Okay.
Okay, and then these two, and then whoever's biggest will go to the left, its head. Okay, swap please.
There we go.
and then
Okay, and now we're at the end.
And then we'll start again until
Oh, we're going to start again?
yeah. But
Why
they're
would-
like in the
Why are we going to start again?
until they're in the correct order.
How many times do we have to do it till they're in the correct order? You said before.
oh 6.
Oh yeah, because if we do this process as many times as there are.
Yeah.
Okay, so let's go to the other end. Oh, you're tiring me out.
Oh, I'm tired.
Yeah, you're tiring me out. That's how this works.
And then open again. And then whoever's the biggest one will go to the left.
Wait, you weren't allowed to do that.
Oh, no, do swap.
You're allowed to swap.
Swap,
You just
swap,
can't
yeah.
tell them the
Sorry,
bigger.
swap.
Okay, swap.
Oh, yeah, okay. And then open. Swap.
And try and stay a little on this side so that.
Oh, sorry. Open. Swap. Swap.
You're being demoted.
Swap. Oh, wait, no. No, there's swap.
Don't swap. Okay, now what do we do? What do we do, Charlene? I'm having a panic here.
Start from the side
Oh,
again.
thank God. Okay. Let's do this.
Okay. Swap.
Okay.
Okay. Open. Stay. Okay, swap. And cut.
Oh, we're done? How do we know we're done?
Oh, we will look at all.
Wait, how do we know we're done?
Oh,
Well, we made some swaps, so how do I know that when I go back, there aren't going to be more swaps to make? I think we should go back and check. Okay, so let's see. Let's go from the start.
okay. Okay, so don't swap. Okay. Don't swap. Don't swap. Don't swap. Don't swap.
So tell me, again, in your intelligence, how did you know that we were done?
They're not in order.
Well, you couldn't remember all of that. I know I certainly couldn't. But when we were doing something, we didn't make any Yeah, we didn't make any swaps. And so if we didn't make any swaps, that means that, yeah, it's done, because there was nothing left for us to do.
Yes.
My, you really are a big brain, Charlene. We're so lucky to have you in our class. Can we have a round of applause?
I think I left some hair in there, sorry.
That's okay. The big brain has had worse. And a big round of applause for all our remaining volunteers. Maria, Perrin, Ruben, and I can't see who's next. What was your name? Ket? Jack, Oscar, and Charlene. Big round of applause one more time. Thank you, everyone. Okay, you can all head back and put your numbers down. So it seems we have a few different ways of doing our sorting. In fact, we used two different algorithms. The first time the algorithm that Charlene used was to go through, look for the biggest thing, and move it to the far side. Then leave that one there, go through again, look for the biggest thing, and move it to the far side, and then you leave the two biggest ones. Then go through again, find the biggest one so far, and then move that one to the end. Do the same thing, and so we have a whole bunch of different sorting algorithms, and we're going to go through at least a few of them in this class. I'm not going to step through the code for all of them. Let's pick the code for the one that Charlene did second. All of these basic sorting algorithms are going to have the same rough outline. We're going to go through, look and determine whether to do swaps, go through and look whether to do swaps, 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 and look whether to do swaps. Okay, we'll do insertion sort, because that's one of the ones that we did live. It's always a little unpredictable what sorting algorithm the person at the front of the room is going to pick, because there are a bunch of different ways to do it. Okay, so the way this one works is, firstly, let's just assume that our array is all set up correctly, because otherwise we're going to get into trouble. And we are going to use our swap function. This is pretty much as you saw before, except now we are going to be swapping array elements. And the way we do that is we're going to take the index of two neighboring array elements. So this is one on the left and one on the right, a of j and a of j plus 1. And we're going to get their addresses, because if we just use this syntax, that'll get their value. So as a reminder, that is an address, this is a value, that's an address again. You'll have to play around with it before you really get comfortable. So get the address of the two items and feed them into the swap function. The swap function will copy those addresses and then do the swaps of the things at those addresses. Okay, so there's something there. Now what we're going to do is we are going to start looking at the second item in the array. So remember, index, when I is equal to 1, the array actually starts at index 0, so looking at index 1 is actually looking at the second element in the sequence. So we're starting from the second one, and where are we going up to? We're going up to the end of the array, where I is less than n, and n is the length of the array. And you'll notice this function, sort int array, has two parameters. It has a, which is the array itself, and this is the syntax, the function declaration syntax for passing an array. And we also have how large the array is, because C doesn't actually keep track for us of how large the array is. So we're going to go through it n minus 1 times, because we're starting at the first index, at index 1, which is the second item, and going all the way to the end. Then what we're going to do is we are going to continuously swap that element left in the array until we are sure that we shouldn't make a swap. So remember, one of the things that Charlene was doing was at every stage she was looking at two neighboring items and deciding swap or not swap. Now this is kind of the same thing. It's a slightly different algorithm because we're looking for one item at a time and swapping that one item continuously along till it's in the right place. But the basic idea is the same. Look at the two items next to each other, have them turn around, swap or not swap, and you move it over continuously. Okay, so what about our j variable? In our j variable, we are going to start at the item to the left of I. So if we have our item at 0 and our item at 1, our I will be the one at 1, and our j will be the one at 0, and then what decision do we have to make? Swap or not swap. And how do I know whether to swap or not swap? Agrim? Which one is bigger? So in this case, what am I doing? I'm checking to see if the one on the right is smaller than the one on the left. If the one on the right is smaller than the left, then I am going to, the one on the right is smaller than the left, then I am going to make the swap. Once I've made that swap, so let's imagine I'm doing this with item 0 and item 1. If I've made the swap, I now have the bigger item is in position 0, but there's nothing to compare it to on the left. So I'm done with this round of swapping. Okay, now I make I bigger, and I know that the item on the far left is smaller than the one immediately to its right, and I move over, and now I've got 3 possible items that I could look at. So I'm looking at item 3, which is at index 2, and I look at the item next to it, and what decision do I have to make? Swap or not swap. And I decide based on, Emmeline, you know the answer to this one. When do I decide to swap or not swap? Yeah, so when the one on the one on the right is bigger, other way around. So when the one on the right is bigger, I make the swap, and now I've moved over and compared the 2 items again. I'm comparing the 0th item and the first item now, and what decision do I have to make? Crystal? Yeah, which one is bigger? Do I swap or not swap? And let's say that this one is still bigger. I make the swap, and now I know that the biggest one so far is in the leftmost position. The next biggest one is in the next position over. And if I repeat this as many times as there are objects in the array, then I'm guaranteed to be done, because you can't keep swapping items into the biggest position more times than there are things to sort. And that's essentially all that is happening here. So make sure that j is bigger than 0, because otherwise you'd fall off the end of the array. Check which of the two, check if the one on the left is bigger, and if you should make the swap. If you should make the swap, do it. And then decrement j, which means look at the next item along and determine swap or not swap. And that is the entirety of insertion sort. Let's just look at 1 or 2 last things to clean it up. We have a function here that prints the array. And so all this does is it goes from 0 to n, where n is the length of the array that's being passed in as an argument, and then just prints the objects. We have our int swap, which is the same as before. And then we have our main function, hopefully somewhere. I might have passed it already. Our main function gets you to enter up to d value, enter as many integer values up to some maximum. And if we look at the top, we have a maximum of 10 values because we have to define the size of the array ahead of time. So we have some code there to read it in. If you do give it more values than it has room for, our program is clever. It detects that by counting how many items it's read in so far, and so it'll just throw the rest away. And then it will hopefully, oh, there's our main function. It reads in an array, it prints the array, it sorts it, it prints the new array, and let's give it a look, and that'll be the last thing for today. Give me some numbers.
42.
Come on.
20.
20. 7. Oh. -1. Oh, let's stay away from the negative numbers from the time being, even though it will work. Oh, there's -1. Yeah. Come on, this is the easiest part of the class. One more number. 35, 31, okay. Oh, I pressed enter, it didn't work. Why didn't it work? What do I need to do? Control D, okay, let's do that. And now I have a sorted array. And thank you very much to all of our participants for today. A special thank you to Charlene in particular.